I do want to say, I don't have the schedule up because I'm a lazy butt, but that's okay. I'm going to put the schedule up a little bit later. Your major assignment is due on Wednesday, December 4th. Is that what it is? Yeah, third. No, second today. Yeah, it is. Okay, second, third, fourth. Perfect. So your major assignment is due on the 4th. You should be able to finish all the questions as of the end of class today, but we'll see how much information we get to. Then you're going to have your exam on Thursday, and then there's no class on Friday. Tomorrow I'm going to give you an information sheet that lists all the information about exam rewrites. Now, over the next 3 weeks, you can pick one of your exams. I'm not forcing you to do this, but you can pick one of your exams that you feel like you did either like less well than you're capable of, or you feel like you just didn't know it at the time, but maybe now you know the information better. So you can pick one exam, and then sometime in the next 3 weeks, and you can rewrite it before the Christmas break, and then it will not quite replace it. I'm going to talk to Mr. Zakowski and see what ratio we're going to agree on, but I will give you that information sheet tomorrow, if that's okay. Cool. So major assignment due on Wednesday, and then we're going to have our exam on Thursday. Today is all about activation energy. Shelby, question?
This is about our exam schedule. Does that mean that if they're rewriting, essentially we have three exams before Christmas break? If you're rewriting one of them, and then we have this one, and then we have another one yet?
We don't have another one before Christmas break.
Okay.
Your last. I was hoping we could get the organic chemistry one done before Christmas break, but we're not going to be able to. So it's going to be like the Thursday or the Friday that we get back from the break.
Okay.
Which is going to be unfortunate because your brains are going to melt over the 14 days or 16 days that you have off, right? So, but that's, I don't know, we'll see how it goes. That'll be fun. So yes, if you choose to rewrite, you will have 2 exams in the next 3 weeks. Yeah. Your diploma is, let me get this straight, January 28th at 9 a.m. in the BAM gym.
So we have a lot of time.
Yeah, it's Tuesday, January 28th in the BAM gym at 9 o'clock.
What time? 8 a.m.?
9.
8 a.m.
Sure.
Yeah, sure. I mean, you can show up
8
at
a.m.
still have 3 hours.
Yeah.
9 a.m.
Yeah.
That's good. In grade 9, we have a couple weeks, then we get 2 years of graceful.
Our district has chosen that all government exams will be written at 9 o'clock in the morning. Now, we don't have any leeway on diploma exams. Diploma exams, if they're starting in Grand Prairie at 9 o'clock in the morning on a Tuesday, then that exact same exam has to start at 9 o'clock in the morning in Lethbridge on the same day, right? There's no leeway for diploma exams, but each district gets to set their own schedule for PATs. So we could write our Science 9 PAT 5 days after the Catholic Calgary system does, or whatever. It doesn't really matter. PATs doesn't matter. Yeah, because it's grade 9. Nobody cares. It's not human beings yet. Yeah, no.
Do they just share about cheating in grade 9?
Yeah, they're assuming that there is no systemic cheating problem at the grade 9 level, because grade 9 it's not that it doesn't go anywhere, but there are no huge ramifications. It's not like universities are looking at your grade 9 PAT mark and saying, well, you got less than 85%, we're not going to let you in, you know what I mean? But they very well could be doing that, right? For Ivy League schools or something, they could look at your diploma and 10 marks and say, you got under this, so we're not going to let you in. Okay.
Look at your diploma marks.
No, so some universities Some universities, depending on where that university is, they could consider just your diploma exam.
Seriously?
Yeah.
So if you
But-
had like a 15 in class, you would have an 8 on your phone.
Yeah, they could just consider your diploma exam mark. Now all of the Canadian post-secondary institutions that I know of, they take your blended mark, which is your 70% in class and your 30% diploma exam. But I know of some institutions in the United States that just to try and because in the US they use SATs for entrance into university, right? And so the most comparable thing to SAT is the diploma exam. So that's what they do. I don't know, hopefully that makes sense. Anyways, today is all about activation energy and catalysts. So you should already know that many chemical reactions do not proceed without a little energy to kickstart the reaction. One explanation of why this occurs is called collision reaction theory. So you have this split up, it's on the same page, but it's split up along 2 slides for me, so I'm going to have to go back and forth and back and forth. So you can, when particles collide, you can kind of think of it as, well, sometimes when they collide, they don't react at all. So sometimes when they collide, the carbon monoxide and this nitrogen dioxide, this thing collides with that thing, they smack into each other, but there's something wrong with the collision. Either there's not enough energy behind the collision, or they're not oriented in the appropriate way. And so you don't get an effective collision. There's no transfer of energy, there's no change in energy, there's no transfer of electrons or atoms or anything like that. In order to have an effective collision, you need to have the perfect orientation of molecules. You need to have the perfect amount of kinetic energy behind both molecules. And so conditions need to be just right in order for this thing and that thing to collide in the perfect way, to react with each other, and then you'll get a transfer of atoms or electrons or energy or something like that. Yeah.
You're gonna laugh at me probably.
Sure.
Kind of like people in the hallway. So
Yeah.
like you bump into them, you're not going too fast. They're not gonna say anything. But
Totally.
If you're sprinting,
Yeah.
you hit someone, they're gonna say something, right?
Yeah. The analogy we've used in the past has been like you and your best friend develop a super secret like handshake or whatever. And so in order to do your super secret handshake in the hallway, is that doing your super secret handshake just me and Maj, we just develop a super secret handshake, right? So what do we got to do? What do you want to do first? So we're gonna do a fist bump, okay? And then we're gonna smack back and back, and then we're gonna do this, okay? So yeah, I love that. Yeah, the palm up. Okay. Yeah. So we're gonna do a fist bump, and then we're gonna go back and forth and. So, in order for us to do that, right, we have to be, if we're walking past each other in the hallway, in order for us to do that, we have to be oriented in the perfect way, right? If he's coming at me like this and I'm going across like that, it's going to be really hard for us to do that in the heat of the moment, okay? If I'm sprinting down the hallway and he's not moving fast enough, then we're not going to collide in the right orientation. If we're moving too slow, then I'm not going to be in the appropriate location to be able to do that. So there's lots of ways to get an ineffective collision, but only very certain ways to get an effective collision for us to be able to actually react. So certain conditions are some particles that move randomly. Collision reaction theory has like a bunch of things related to it. Some particles that move randomly and bounce off each other, sure, okay. A chemical reaction must involve collisions, sure, that makes sense. Successful collisions require sufficient energy. If they're not moving fast enough, you can't transfer those atoms. Collisions with the required minimum energy have the potential to react. An effective collision requires appropriate orientation, so bonds can be broken or formed. Ineffective collisions involve particles that rebound off each other. Some reactions occur more readily than others. Okay, no problem. And so there's lots of factors in here, But at the end of the day, let's think about this. Are there any bonds being broken in this reaction? Let's look at the effective reaction, an effective collision. Are there any bonds being broken? Look at the beginning and look at the end, and let's see, are there any things that used to be together that are no longer together?
Yes.
Yes, what?
Gray and
An O used to be attached to what? The nitrogen. So in order for this reaction to occur, what bond has to be broken? The nitrogen-oxygen bond. Okay? So this nitrogen-oxygen bond must be broken. Are there any new bonds that are formed? Are there any things that are attached to each other that didn't used to be attached to each other? Yeah, we started with a CO and we ended up with a CO2. So what new bond was formed?
oxygen bond.
Yeah, a carbon-oxygen bond, right? So there's this bond between the carbon and oxygen that wasn't there before. So a carbon-oxygen, it should be a double bond, but whatever, that's fine. The carbon-oxygen bond must be formed. In the middle, there's something that we call an activated complex. What that means is you're halfway between breaking this bond and forming a new bond. And this activated complex is extremely, extremely unstable. Now, when you think of things that are unstable, should they have really high potential energies or really low potential energies to be really unstable?
High.
Really high. Remember, think about putting things on a really high shelf. It has the propensity to fall off and give off a lot of energy. So potential energies that are really high are super unstable. We can graph this the way this looks. And so the reactants are going to have a certain amount of energy. The products are going to have a certain amount of energy. But which three of these things has the most potential energy? The activated complex. It's the most unstable. So this activated complex is extremely unstable. What that means is it's got a really high potential energy. Okay, well, let's take a look at the next page. And let's graph what happened in that previous scenario. So some reactions, they need that extra bit of kinetic energy, right? Two particles that are just sitting side by side, right? They're just sitting in contact with each other. Do they have enough energy to react with each other if they're just sitting there side by side? No, they need a little bit of energy in order to actually react. And so what we're going to do is we're going to say, okay, this is the potential energy, right? We're going to draw a potential energy diagram. So on the left side, on the vertical axis, that's potential energy measured in kilojoules. On the bottom, do you remember what we put on the bottom for a potential energy diagram?
Reaction over.
We say reaction coordinate, or sometimes we say reaction progress. So the progress of the reaction. So in here we've got our reactants. And at the end we've got our products. I'm curious, in order for this, what does it look like this reaction is going to be? Is this going to be Endothermic or exothermic?
So it's going to be X.
Is our system from beginning to end, is it gaining energy or losing energy? That's losing energy. So that sounds like an exothermic reaction. Well, remember, in order to go from reactants to products, what did we have to go in between? What did we have to get to?
Yeah.
The activated complex. So what that means is that in order for us to do this, we actually have to gain potential energy. We're going to temporarily turn the kinetic energy of the collision into potential energy of our activated complex. Now we can define how much activation energy is required in order to do this. All we have to do is figure out what's the difference in energy between there and there. This is, and we say EA for activation energy, just like EK is kinetic energy, EP is potential energy. What's EA?
Sports.
Yeah, EA Sports. Get in the game, right? So EA, that's activation energy. But I want you to think about this. Let's go back to our equilibrium days. Can reactions only proceed in a forwards direction? No. So think about this as you're trying to drive over the hill, and so in order for you to actually get to the other side, you need to overcome this activation energy. Now, is the activation energy greater in the forwards direction, or is it greater in the reverse direction for this particular reaction? The activation energy is much greater in the reverse direction. Here, this is the activation energy in the reverse direction. Direction. So this is the activation energy in the forward direction, while that's the activation energy in the reverse direction. Perfect. Overall, is this reaction endothermic or exothermic? It's exothermic. And remember, how do we determine the total enthalpy of a reaction? What is it? It's
The sum of the final.
the sum of the products minus the total sum of the reactants. So really, the enthalpy is really just this, right? That's the enthalpy for the reaction. Does the activation energy affect the enthalpy at all? No. It's a lot like if you're a physics person, and it's the difference between distance and displacement, right? The enthalpy is the displacement of the reaction. It's what did you have at the beginning versus what did you have at the end, and you don't care about what happened in the middle, right? So this is our enthalpy of our reaction. Now, I know there's a lot going on in this diagram. I get that. There's a ton of information that we can get out of a potential energy diagram. And we'll talk about a couple examples here. So let's talk about endothermic versus exothermic. At the top, what do you want it to be, endothermic or exothermic?
Endo.
Sure, endothermic. And at the bottom, let's do exothermic. So who has more energy for an endothermic reaction? Do the products have more energy or do the reactants have more energy? So endothermic, is my system gaining energy or losing energy? Gaining. It's gaining, so that means our products have to be here and our reactants have to be here. And so our activation energy will always be more energy than the products. Remember this? This is our activation energy in the reverse or in the forward direction. Whereas this is the enthalpy. So is our enthalpy positive or negative when we're endothermic? Positive, right? We're gaining energy. The system is gaining energy. And then for exothermic, well, it's exactly like what we just did in the diagram before. Our reactants have more energy than our products do. But there's still got to be some sort of an activation energy. This is our activation energy. And this is our enthalpy. So our enthalpy is negative. We already talked about a lot of this stuff. I can't remember what I was going to write from here, but I think that's pretty straightforward. I think on the next slide, I think it's a question that I want you to answer, isn't it? Yeah, there we go. You go right ahead and do this. Go try it out. This is a really complicated question. Look back at your notes and just try and figure this out. But this is a really complicated question.
Oh, it's not that. Oh, the second part.
Drawing a diagram is going to be very helpful for you.
I don't know how to piss or what.
You know what this sounds when you draw a diagram? If it's got a small hump up here, sometimes it's going to go down like that. You know what that means? It's exothermic.
It was a 3-minute.
It's exothermic. I'm so hungry. I could eat a whole loaf of bread.
Why is this one different than this one?
You want to go buy bread together?
Keep this line up here.
Oh,
No, I know what that is. When you compare them, I hate it. I hate it. Also, this is not. These are forward. I thought this was forward.
No, it's based on the. It's based on this is.
Oh, never mind. No. But then,
It's excellent. Like I told you, because the pump goes.
I wasn't even talking about this.
Basically, if the forward is smaller.
I'm not talking about
the
this
top and the
either.
bottom, the bigger gap between top and bottom. This way is
Why are you trying to explain it to me?
What do you have? Do you have food?
I'm talking about these.
Reactants are always on the left.
The big gas. I can eat a whole thing of big gas. Yeah. I'm not gonna buy a big gas.
Yeah. Okay, what else?
Bro, they're like
This. Trying to scale them so bad. Putting them into a bag is so bad because like I'll try every bag I try to make it a stable spot, right? So I'll put a bag in there and it will just like slog over and I'm just like, oh no.
So draw me your
Yeah.
so many shapes. yells at me if I do it wrong. She always regrets.
Denver.
Oh, I'm scared.
Oh,
my God.
I'll put $2
You selling your car?
Great spinach.
Probably on my leg. So does the same thing happen to you?
Can we have a party?
I'll bring it back.
I said FOP. I don't even know what orientation is.
I hit it too far.
I think it's the difference. Because look.
I hit it too far. Look at the picture. This is a bit. There you go.
This is like down tree.
Yeah, it would be 10.
Okay.
How many times do I speak?
I'm smarter
When I
than
speak something, you listen, and then you try to educate the other people that already know. That's why I'm yelling at you.
That's what
I'm sorry, I'm being so stupid. Get the point across. Dude, I'm gonna be so smart.
I think we'll take physics.
I'm only good at biology.
I'm good at every.
I'm ridiculous and math 30 at the same time.
No, don't do that.
You're gonna get started.
It's because you need a complete math.
Okay,
No, I don't.
let's try this.
Calculus, calculus.
Like less than once a week. Yeah.
She said it's not a privilege.
But that's only because I'm a lazy guy.
She's not calculus apparently.
Oh, no.
And because I can't grow a beard. I mean, you guys have seen my beard, so I can't grow it. Okay. Yeah, thanks, man. Tell my wife I said that. Please. You don't know your. I love my wife.
But
You wish
But-
she was a curling.
She like.
She doesn't like curling.
No, she
She's
like
gonna get it.
almost hates curling. The
Yeah.
only reason she likes curling is she likes to go and make fun of me when we curl because of how much I like. Because of how much I like. Curling. Yeah, it's super healthy. Okay, let's think about this. So, the activation energy. The activation energy in the forwards direction. Remember, that means how much energy does it take to get over the hill. So if this is where my reactants are, and this is where the top of the hill is, then how much energy does this represent? This represents 30 kilojoules. Now, from the other perspective, did it take more energy to go the reverse direction or less energy to go the reverse direction? So it took more energy to go the reverse direction, right? So is this an exothermic or an endothermic reaction? This is exothermic. Perfect. Now, what I want to know is what is the enthalpy of this reaction? 10. Good. Because you would have to add another 10 kilojoules to get down to there, right? So the enthalpy is negative 10 kilojoules. Hey, that negative's pretty darn important, right?
Because it's exothermic.
Hey, was that a difficult question? No? Alright. Perfect. Answer me another question. I'm gonna give you 30 seconds to answer this one, but I'm gonna go back. Yeah. What? Yeah, it is.
Where's it gonna hit?
Oh, it's gonna hit everywhere. But the epicenter is in my hometown of Edson, Alberta.
I don't think that's a good thing.
That's what not a good thing.
Bring it to the ground.
Wait, how? Why is Calgary so far down?
When is this?
Calgary's supposed to be that far down. Calgary, realistically, Calgary is approximately this far down.
And Edmonton's right here.
Yeah, and Edmonton is actually lower than
Central, Bruce.
Well, yeah.
Like
it's
Edmonton is properly in central Alberta. If you were to split up Alberta into like 3,
and we're in the middle of this, right?
yeah, and so
No one.
realistically, Edmonton
Literally
should
no
be
one.
kind of down here,
Yeah.
and
Fort Mac.
then
Fort Mac is
Red Deer
in
should be in the middle, right?
So like, are we gonna get to feel it?
What?
Are we gonna feel it?
Well, it depends on the magnitude of the
Are we
earthquake.
actually getting it?
When is it? No, we're not. No, we're not going to get an earthquake.
We're talking right now.
What? Because we were talking about it in Science Funny.
Okay,
I was
why didn't you
saying,
just say that's radio
saying,
wave?
I hope this doesn't happen, but let's say my hometown of Edison is at the
You'd be like,
epicenter.
heck yeah.
Yeah. And then I wanted to say which municipality would feel the earthquake first? Edmonton, Calgary, or Medicine?
Edson would.
Edson, yeah, after Edson. So Edson would be leveled by the earthquake, okay? Who's next? Edmonton, yeah.
And
then
Red
Technically Knighton Junction first, okay? Then,
What?
yeah, I went to Knighton, yeah, I went
There's more
to...
cities than Edmonton, Calgary, and
Okay, anybody get an answer? Mr. Vesley, yes.
I got D. Require more than the reaction density to start.
Good. Okay. So is this indeed endothermic? Yes. And what's greater, the reaction enthalpy or the activation energy? Which one's greater, the activation energy or the enthalpy? The activation energy. So it would require more energy than the enthalpy to get it started. Okay, we're gonna define something a little bit more.
Why is the earthquake?
Why is the earthquake?
Okay.
Why is the
So, what I want to bring to your attention is that I've got some molecular models here, and what I want to happen is I want this. This is a chemical called dimethyl ether, and this is a chemical called water. So, what I want to happen is I want dimethyl ether to turn into something, and I want the water to turn into something. So when these two react under certain conditions, what we can get is I can take this off of there, take that off of there.
I love this is a very fast reaction.
Yeah, it's a very fast reaction. And I can get basically two of the same thing. I've got two methanols here. Okay? Now, somebody describe for me the two things that I had to do in order to react them to break or make bonds. Break bonds. The first thing I had to do is break bonds. Now, atoms or ions are a lot like magnets, okay? Atoms and ions are drawn, they're naturally attracted to each other. Because at the center of an atom, you have a positive charge, and on the outside of an atom, you have a negative charge. And so the positives in one atom are attracted to the negatives in another atom. And so atoms are naturally drawn towards each other. So you can think of a molecule as a stack of magnets, and the bonds are what keep them together. Now, when I break bonds, does breaking bonds require the input of energy? Or does breaking bonds naturally release energy? What do you think? Does it? Is this so let's think about this. Bonds can either break or bonds can form. Which one was a more natural process that seemed like it either released energy or yeah, okay, so forming of bonds releases energy, right? But in order to break these apart, do I have to put energy in to break these apart?
Yes, sir.
Yes. And so what we can do is we can represent this potential energy diagram of this reaction in a very specific way. So chemical reactions involve the breaking of old bonds and the forming of new bonds. Breaking bonds is difficult. It requires energy. So what does that mean? When I break bonds, does that mean an increase in potential energy, or does that mean a decrease in potential energy? When I break bonds, am I giving the system energy, or am I accepting energy from the system? When I break bonds, is this giving energy to me, or am I giving energy to it?
You're giving energy.
I'm giving energy to it. Okay? So breaking of bonds, the breaking of bonds can be represented by a steep increase in potential energy. I'm showing the reason why this isn't a curve anymore is I'm showing two very discrete processes. Okay? I'm trying to show one process and then another process. And so if this is my reactance, this represents the breaking of bonds. This also kind of represents the activation energy in the forwards direction, right? This is very similar to the activation energy in the forwards direction. Okay, then when I go to make new bonds, so I broke these bonds, right? And now I'm going to try and make new bonds. Does this happen very naturally, making new bonds?
Yeah.
Yes. So is the system giving away energy, or is it stealing energy from its surroundings?
Stealing energy. Oh, the other one.
Is the system, are my magnets, are they absorbing energy from its surroundings? Do you have to force this to happen?
No.
You don't have to force it to happen. They just have to be under the appropriate conditions for it to happen. So does that represent the system losing energy or the system gaining energy?
Losing.
The system losing energy. So this represents bonds being formed. So it requires energy to break bonds, but then energy is released when you form new bonds. Now, can you understand, is it fairly easy to see that endothermic and exothermic reactions are a result of which one of these processes was greater? Right now, which one of these processes, the breaking or the making of bonds, which one involves a greater energy change? The making of bonds. So did that result in an endothermic or an exothermic reaction? That resulted in an exothermic reaction. Does that make sense? But if let's say if the making of the bonds was much smaller, I'm going to write this, but you don't have to. Let's say the making of the bonds involved a much tinier energy change. Would this be endothermic or exothermic now? This would be endothermic because it required us to put in a certain amount of energy, but then we only got back a tiny amount of the energy we put in. And so that means overall it took more energy as opposed to releasing energy. Hopefully that kind of makes sense. I'm just going to get rid of that. Perfect. So let's take a look at this. In the reaction below, what involved the greater energy change? The making or breaking of bonds? It sure looks like the bond making process involved the greater energy change, right? Bond making was way higher than bond breaking, right? Therefore, the reaction is exothermic. And we could say this. We could say that for any reaction at all. We could write that. Depends on, you know, is the bond breaking bigger than the bond making, or is the bond making bigger than the bond breaking? That's all. Any questions about that? Okay, catalyst. Kind of want to talk about this tomorrow. What I would like you to do is I would like you to either spend the next 25 minutes working on your major assignment review booklet, assignments, or your, there's lots of practice diploma questions to be able to work on. And if you're done all of that stuff, don't go yet. If you've done all of that stuff, what I would like you to do is by the end of tomorrow's class, please read through tables 1 to 4 on pages 539 and 541 about catalysts. Just read through them, and then tomorrow we're going to talk about catalysts, and we're going to see a reaction that requires a catalyst to actually happen. I'm going to perform a demonstration.
Mr. Walton, your demonstration.
Oh, thanks, man. Yeah, Alicia.